Okay, so here, why does this reduce the variance? Let's take a very simple example. Let's say I have the event A and have the event B. And let's assume the event B actually captures majority of the event A. So that basically event B happens for 1% of the time, okay? And the event A happens for 1/10,000th of the percent of the time. But most of this 10,000 is actually contained in the event B. All right, yes? Why do we have the
equation of variance?
Oh, here, right? Yeah, this is because if you so here, this is a random number, right? Because we are having our estimate. The first term is a random number, the second term is a deterministic number. So if you look at the variance of a random number scaled by a deterministic number, that is equal to the deterministic number squared times the variance of that random variable. Right, so that's because you have the property of variance of lambda x equal to lambda squared times the variance of x. Yeah, you can simply do that by looking at expectation of lambda x squared minus expectation of lambda x squared. You can see for both terms, you can pull the lambda out, and the lambda becomes a lambda squared, right? Okay, so let's imagine I have the two probabilities, and in here, when A and B both happens, it's actually 9 out of 10 times when A happens. And here we only have when B does not happen, there is 100,000th of the probability of everything that so basically when B doesn't happen, A is much less likely to happen. All right, and okay, so then the variance becomes the probability of B, which is 1% squared, right, times the variance of P conditional on A, and the the probability of A conditional on B is this probability multiplied by 100, right? So this conditional probability is so P of A condition on B is 9 over 1,000. So here the variance is also the same, so 9 over 1,000. And then the second term is the probability of B squared is B naught squared is 99 over 100 squared, which is close to 1, right? And times the variance of this probability. The variance of this probability is also the probability of A given not B, which is going to be 1 over 100,000. So 1 over 100,000. So this probability, if you count this as 1, okay, it'll turn out to be, so this is 9 millionths, this is 10 millionths, so it's going to be like 19 over a million. So that's the variance of this estimator. While if you directly estimate using this Monte Carlo method of directly the probability of A, what you get is the same as the probability of A, which is 1 over 10,000, right? So if you compare these two numbers, the variance of this important sampling estimator is 10 times as small as the variance of directly estimating the probability of A. And Yes.
How did you go from P of A given B to variance of P of A given B?
Oh, this is because the if you estimate a certain probability, the variance of that probability is with one sample, right? Is actually the probability itself. If the probability is a small probability. I mean, strictly speaking, it's p times 1 minus p. But if p is small, you can substitute 1 minus p to 1. So the variance is roughly the same as the probability. All right. Actually, this is about five times smaller than that probability, right? And basically, it allows you to have 5 times less samples and still have the same variance.
A thousand is what about the P of A given B 1 over 100,000 what?
Which term? This one?
So
Or
the P of A given not B is 1 over 100,000, but P of A given B is just 9 over 1,000, not 9 over 100,000. I'm not sure I understand. So like you went from 1 over 100,000 and you said that the probability of A given not B is also 1 over 100,000. Right? But for probability of A given B, we decreased the denominator became 1,000, not 100,000.
yes. So this is because the B has 1% of likelihood happening, right? So this is the probability of A and B. This is the probability of B. This is the probability of A and not B. So the probability of A given B is the probability of A and B divided by the probability of B, which is 9 over 1,000. The probability of A given not B is the probability of A and not B divided by the probability of not B, which is 99%. So I kind of neglected the 99% here. It should, yeah. All right. So I went pretty fast at the end. All right. So in conclusion, if you find yourself need a huge number of samples, think about importance sampling. So try to find out another variable or another event that is highly correlated but much easier to sample, right? So much easier to predict and sample. And use the importance sampling, you can reduce your number of samples by a huge factor. All right, cool.